Hello everyone, my name is Mehmet Seyfioglu and I'm a fifth-year PhD student at the University of Washington, Seattle. Today I will present our CVPR paper on training a large language and vision assistant for histopathology. So the TLDR of our work is that we trained Quilt-LLaVA, a large language and vision assistant, which outperforms state-of-the-art on various benchmarks. To do that, we curated a novel dataset where we leverage educational histopathology videos from YouTube. Large Language and Vision Assistant, or LLaVA, is a framework that has shown tremendous success in various multimodal chat capabilities in natural domain. LLaVA is trained by generating an instruction tuning dataset from spatially grounded datasets like MS-COCO. The instruction data is often generated by a large language model such as GPT-4 using image captions and object bounding boxes. Following the success of LLaVA in the general domain, the medical community quickly followed suit with models such as LLaVA-Med. Although in some relatively simpler medical modalities like X-rays, LLaVA-Med seemed to be providing sufficient performance, it is not so successful in relatively more complex fields like histopathology. For example, it can't spatially locate histopathological concepts. Even worse, given evidences, it cannot reason properly beyond the current image patch, limiting its diagnostic capabilities. But why is that the case? Long story short, because it leverages PubMed to generate instruction tuning dataset. So they curate figures and captions from PubMed articles as shown in this example. And unlike MS-COCO dataset with object bounding boxes, PubMed articles lack spatial groundings, making it difficult to ground histopathological concepts and reducing their usefulness. Also, PubMed images are isolated image patches that lack holistic whole slide image level understanding. So we need a better dataset than PubMed-generated image caption pairs. So what to do? Instead of relying on PubMed, we propose leveraging the advantages of educational videos, where narrators often utilize their mouse cursors as they explain histopathology concepts, so we can visually ground their words by capturing these mouse tracers. Furthermore, videos generally showcase multiple patches from a single whole slide image, as narrators typically traverse the whole slide image, zooming in and zooming out, thus providing a holistic understanding over the whole slide image. As shown in this example, the narrator traverses the whole slide image and showcase particular regions with their mouse cursor as they explain the concepts that they see. So using Quilt videos, we devised the technique to automatically capture the mouse tracers of narrators to visually ground their words. We observed that in educational videos, narrators pause while exploring whole slide images before highlighting the areas with their cursor. We identify these stationary frames using our handcrafted distance-based algorithm, which uses pixel-wise absolute difference and SSIM to measure the distance between consecutive frames. So we hypothesize that if the background is more or less stationary or unchanged through a couple of frames, then the narrator is typically showcasing something of importance here. Then we find the medium frame in each stable chunk and subtract it from each frame to locate the mouse cursor. And finally, we employ spatiotemporal clustering to map cursors to narrator's speech. And in the end, we have this right-hand side image description here, where we have some speech and a bounding box that localizing that speech into image. So after curating our visually grounded dataset, we move on to generate an instruction tuning dataset. We use two different categories of prompts here, independent and reasoning-based. For independent prompts, similar to LLaVA-Med, we use conversation and detailed description-based prompts. These are called independent, where each image caption pair is considered to be independent from one another. The objective of a conversation prompt is to construct a dialogue between an AI assistant and a human inquiring about the histopathology image. Similar to LLaVA, we use GPT-4 and image description to generate this question-answer data. And similarly, the aim of the detailed description-based prompt is to provide a detailed observation of the image. And then we have reasoning-based prompts, which aim to extrapolate beyond the given image to reason for diagnosis. And in complex reasoning of the reasoning-based prompts, given a caption, along with the diagnosis and supporting facts that are extracted from the broader video, we prompt GPT-4 in a diagnostic reasoning task designed to extrapolate beyond the immediate context of the given caption. More broadly, We instruct GPT-4 to utilize its inherent medical knowledge to interpret the contents of a single image caption while subconsciously incorporating the diagnosis and supporting facts extracted from the broader video. In iterative abductive reasoning, we create a framework where two GPT agents are conversating. The first agent, human GPT, has access to a single image patch and it abductively reasons towards a diagnosis. The second agent, AI assistant GPT, has seen the entire whole slide image as we provide it with the entire video context and thus guiding human GPT by providing hints and feedback towards the diagnosis. The conversation continues until a conclusion is reached or the limit is met. Using these four types of prompting strategies, we generate Quilt-Instruct, which consists 107,000 question-answer pairs for histopathology. Then we move on to training Quilt-LLaVA, which consists two main elements, QuiltNet as image encoder and Llama 7 billion as large language model. We follow the same procedure with LLaVA in training, which follows two steps. In stage 1, we train an MLP layer to align the image and language modalities using Quilt image language dataset. And in stage 2, we use Quilt-Instruct to fine-tune LLM alongside the MLP layer while keeping the vision encoder frozen. Since we are utilizing educational videos, we also realize that narrators often pose questions during their presentations and subsequently provide the answers themselves. Collecting these organic question-answer pairs with the help of GPT-4 and some handcrafted algorithms, we gathered a rich evaluation dataset of 1,283 question-answer pairs, which we call Quilt-VQA. Using Quilt-VQA, we then evaluated Quilt-LLaVA against LLaVA-Med and LLaVA baseline using GPT-4 evaluation. Here, we use GPT-4 to relatively compare our model's answer against the candidate model's answer by providing the ground truth. We beat both models across 14 subpathologies. We then used public datasets such as PathVQA and PMC datasets on both open and close-ended question answers, where close-ended is based on multiple answer choice. We also run many ablations such as visual prompting with red circle, so please see our paper to see more details. Our code, data, and models are available in our website. Thanks to my co-leads Wisdom and Fatma and my advisors Linda and Ranjay for their guidance and support. And thank you for your time and attention. Also thanks to Microsoft Research for supporting our work.